Okay, so we'll set it for the 23rd. Okay, so for your test one. Okay, so for today, we will cover one section which is on the synchronous machine tests and measurements of the machine parameters. So we've done that before in electrical machines too, where we did the open circuit test and the short circuit test on the cylindrical rotor machine. So we are extending this basically principle now on this basically new type of rotor that we're working with in Machines3, which is Salient pole. So we will look at how we can determine the parameters of this machine. Remember that in cylindrical rotor, we had only the synchronous reactance to work out. In other words, when we working out this basically this parameter xs, when we basically use the two-axis theory, basically what we've worked out is basically the value of the d-axis, right? So whenever you want to basically simplify the analysis of what we are doing currently with salient pole back to cylindrical rotor, what we do is we equate xq being equal to xd and equal to xs. So basically then we have only one synchronous reactance. Now, so when we separate the two, the principle that we have used before can still be used to determine the d-axis parameter, and the quadrature axis, which is the q-axis parameter, is the one that we have to basically focus on in this section, right? So if you look at this open circuit test, we've done it before. Basically, the stator terminals are on open circuit, and we run the machine at synchronous speed, and we take a plot of the terminal voltage on open circuit versus the field excitation current, right? So we get a plot of what we call the terminal voltage, which is basically now equal to the induced voltage, because it's an open circuit, and we basically vary IF or IX, what we call it, the excitation current. And we take a plot of that, and basically that will give you the open circuit characteristic of the machine. Now, this line, as you can see, I've made a note here. So the terminal voltage basically is equal to √3 times E naught. So that's depending on the type of connection that we have. So usually when the armature is star connected, right? Obviously, then you will have your √3 parameter, and basically, if it's a delta connected machine, then basically it can also be the phase voltage for your machine. So if we measure the terminal voltage line to line, and we want to work out what is the value of E naught, which is the induced voltage per phase, obviously then if you remember, if it's star connected, you basically divide by √3. Same principle that we have used before. Right, so if you remember, if we take a straight line along the slope of the graph before the saturation happens on the machine, you get the straight line, what we call the air gap line. And that's basically the line which is giving you the characteristic of the machine if, there was no saturation in the machine. And the next line is what we call the modified air gap line. And as I explained before in Machines2, so basically we use this modified air gap line when the machine is basically connected to an infinite bus, right? And now if you vary the excitation current, what happens is, because there is current like flowing in your stator, it's basically the induced currents are basically producing a field that's acting against your the field of the rotor circuit. And obviously now with those two action, the field flux and the flux due to the stator currents, they interact with each other, and basically it prevents your stator ion of the machine to saturate. And then what happens is the machine operates along this modified air gap line, so it doesn't saturate. And short circuit tests, as we've done before, same principle on the cylindrical rotor. So you basically short circuit your terminals at the machine, the stator terminal, and we basically start the field excitation at 0, right? Because we have to, we know that there's a short circuit current that's going to pass in your stator circuit, and we basically slowly increase the field excitation until we get rated current to flow in the stator winding, right? And we take a measurement of the short circuit current, and remember that we use that value to basically determine the value of the synchronous reactance for a cylindrical rotor. And here you will see that we will use it to basically determine the value of what we call XT, right? So if you remember, this is what we've used before. So we said the short circuit current is given by basically the ratio of induced voltage that you've measured in the open circuit divided by the short circuit current to get XS, which is now the synchronous reactance for cylindrical rotor. So now when we if you remember, we discussed that principle a bit further, where we worked out what is the difference between saturated synchronous reactance and unsaturated reactance. And we basically used this figure here. And when you want to work out the unsaturated one, remember, you basically assuming the machine doesn't get saturated, and you take the value of EDA. So from this point up to here, so EDA divide by the current, and I to get the unsaturated value. And when you want to get the saturated value, then you use ECA, right? So this is the one here, the rated machine voltage and basically terminal voltage divide by the short circuit current to get this value. So you get two different values. One is EAD and one is EAC, right? So that's the difference between saturated and unsaturated synchronous reactance. Right, so this is basically mostly a revision part for your cylindrical rotor. And now we will look at basically the salient pole section. So as I said, when we work with the salient pole machine, we basically use the same principle to determine the value of XD, right? So what we do is we basically operate the machine same as we've done before with operated at synchronous speed, the rated speed, and we take measurement of your terminal voltage and the current in the stator, the field current, and also then we do the short circuit test, and from there you take the ratio of basically EAD over IAB to get basically XD, and you can work the same for between unsaturated and saturated, same principle as we've used for cylindrical rotor. What is important to note is when your machine is when you're doing the short circuit current, it is clear that the Q component of the armature is 0, and the short circuit current has only the D component, right? So in other words, what we're saying is when we're doing that short circuit test there, the effect of XQ, which is basically in quadrature with your d-axis current, has no effect on the d-axis. Obviously, then it's not participating in the calculation of your d-axis reactance, right? So we can use the same principle to determine XD, which either the unsaturated or the saturated value of XD. And the next part we will basically discuss is what we call the low slip test. Okay, so this is a very important test now, where now it allows you to determine the value of the q-axis reactance. Right. So how it's done? We basically we drive the machine at a speed that's just slightly below the value of the synchronous speed, right? The slip is very low, as you can see, around 0.01. And we basically open the field winding. Okay, so we're not passing any field current in the machine. And we supply the stator by a three-phase source, right? With the voltage significantly reduced to a value of up to 10% of rated value, right? So that we remember now your rotor is basically an open circuit. So when you now apply a voltage to the stator side, okay, at 10% of its rated value, we shouldn't exceed that, because it will basically, if you increase it to a higher value, it will try to pull the rotor into synchronism and operate the machine as a synchronous motor, right? So we want to avoid that. So we run it at a lower voltage of up to 10%. And now, because your stator pole rotor rotates at a slightly different speed than the stator rotating flux, which is your synchronous speed, obviously then the salient pole rotor encounters varying reluctance path, and the stator current therefore oscillates, right? So we will look at how the stator current will oscillate in the next diagram. And from this oscillation in the stator current, we will basically be able to determine the XQ, which is your quadrature reactance. Right. So if you look at the voltage that's across the open field, it will basically be sinusoidal, and basically your voltage applied will basically have this envelope that is also sinusoidal, and the current, right? So the armature current or the stator current will also basically have this envelope. Okay, so based on this diagram, we basically now use this diagram to determine the value of XD and XQ. So normally the direct axis or your d-axis reactance, you can use Vmax, right? So the maximum, as you can see, you have two values. You have one which is at this peak here, and then you have the lower value here, right? So that will give you basically at the maximum voltage, as you can see, the armature current is minimum. So that ratio of Vmax over Imin is here, and that's your d-axis reactance. And when the voltage is at the minimum, you see the current is at its maximum. So that's Vmin over Imax ratio will give you the q-axis reactance. So basically, as we've mentioned, the armature voltage during this low slip test is significantly reduced. And what we do is the measured synchronous reactance XD and XQ are unsaturated at this value because it's operating at a lower voltage. And how we determine the saturated reactance is with increasing saturation level, both XD and XQ will decrease. And obviously, we use the ratio XD over XQ, which basically remains practically constant. Okay, so what we're saying is the ratio of XD over XQ saturated is equal to XD XQ unsaturated. Okay, so now if we basically we are able to determine the values at unsaturated level, which is basically the ratio at those two values using those two formulas above. And as you know that we can determine both the XD saturated and unsaturated using the previous methods. So basically then we can use that to determine the saturated value of XQ, right? So we will substitute those values here and also the saturated value of XD and solve for XQ saturated. So just to recap, basically we can use the previous section to determine the saturated value of the D-axis synchronous reactance, and then basically use the following formula, which is XQ saturated will be equal to XD saturated times this ratio, which is Vmin over Imax over Imin over Vmax, and that will give us this ratio, which is XQ over XD, and then that will give you your saturated reactance of the Q-axis. This is another test that, just for information's sake, we're not going to use it in this course, but it will enable you to determine the open circuit transient time constant, which we'll look at in further sections later when we do the transient section. So it's just basically showing you how using the no-load rotor decrement tests you can determine this this time constant. Okay, so there is another test which is called the retardation test, and here the machine is driven by a DC motor, and we are measuring the armature voltage and current to basically get the input power of the DC motor, and it's enabling us to basically, as you can see here, we can determine the inertia of the synchronous machine, and that will help us to basically look at the characteristic of the swing curve of the machine when we look at the rotor response of the machine. So those last two tests is mostly for transient section, which we will basically focus on those parameters in the transient sections. So we won't need to focus on that. So basically for the salient pole, you can just stop over here, how to determine the Q-axis saturated value of the Q-axis reactance. Okay, so once we've done with this section, I will go through the question, the tutorial question on this section, for you just to have a look at the tutorial question. Right, so if you look at the tutorial on the synchronous machine test and measurement, we have two questions. So I'm going to just post this onto Moodle, okay? And I'd like you guys to basically attempt those two questions, right? And I've given the answers to basically so that you can check your answer. And so in the first part, it's just showing you how you can, if you're given the current minimum and maximum voltages for the from the measurements and the minimum and maximum currents. So it's giving you what is the value of the fluctuating voltage and current there, and you can use that to determine the d-axis and q-axis reactances. Question one, and question two is more detail is provided. It's on a 45 kVA salient pole generator, and here I'm giving you more details in terms of open circuit characteristic, what is the air gap line, and what is the short circuit characteristic, so that you can determine both the d-axis unsaturated and saturated value. And also here we are basically looking at both the value in per unit as well as in ohms. So I'd like you to convert them from your actual value to the per unit value, and also use the second part. So we will use that theory that we've developed for the saturated value of the q-axis reactance to be determined, where you're using the ratios to work out what is xq saturated. So I will post this tutorial now, and then please attempt it, and then we can basically discuss the solution in our next lecture later. Question one, we basically have a three-phase star-connected salient pole machine, and basically we are driving the machine with the field circuit open, and as we said, the stator is basically balanced, supplied with a balanced three-phase supply, right? So and we are basically looking at the minimum and maximum readings on the voltmeter, right? And also the line current fluctuates. So we're measuring the line current. It's fluctuating between those two values. Right, so in terms of working out your d-axis and q-axis reactances per phase, so as you can see there, you need to remember, as we were discussing in the theory part, we are measuring the voltage at the terminal line to line, right? So if the machine is connected, as I said, is in star connected, if you want to get the phase, the value of the reactance per phase, you need to take the voltage that's measured line to line and divide it by √3 to get the phase voltage, right? And since again the machine is star connected, your phase current is equal to the line current, so there is no transformation needed. So from the two values of the voltmeter readings which we are measuring line to line, so I've basically converted them to phase values, right? And as I said, the maximum voltage and the minimum current are used, that ratio, to get the axis reactance, and that comes out to be 5.92 ohms. And for the q-axis, we use the minimum voltage, and that's divided by the maximum current that you're reading on the ammeter, and that will give you the q-axis reactance. Just take note that As I said in the theory part, the reactances that we measure using the low slip test are all unsaturated values. So this will be XD unsaturated and this will be XQ unsaturated. And reason behind that is the voltage that we are using is significantly reduced during this experiment. Right, so this is how you solve for question 1. And as I said, the question 2 basically is more detail provided, where we've been given enough parameters to work out the base values. So using your 3-phase kVA rating and your line-to-line rating of the machine, we can determine the base value. So that's your power SB, right? So this is the apparent power per phase rated, and that will be your base value. So we divide by by 3. And for the current, the base voltage will be the line value, and you divide by √3 to get the phase value, right? And again, to get your impedance, base impedance, you take EB squared over SB, and that is your base impedance value. Also take note that the rated current will be your basically full load current, and so that can also be worked out. I'm just checking now. I think so. We've been given in the question the open circuit characteristic and the short circuit characteristic, as well as the detail of the air gap line. All right. So so from the first part, we've been given, we can use the air gap line to determine the unsaturated value of the reactance. As I said, we're using that formula, which is EdA over the current, the rated current, and that will give us the unsaturated value. And to get the value per unit, I've divided the actual value by the base impedance to get the XD in per unit. Okay. So as I discussed, the ratio of the XQ over XD, right? You can work that out by taking Vmin over Imax times Imin over Vmax. So those values can just be substituted in the equation to get this constant, which is the ratio of XQ over XD. And as we've worked out what is the value of XD unsaturated, right? We worked it out here. It's 0.988. So we can use this constant or ratio K to determine the unsaturated value of XQ, right? And also we can work out the unsaturated value of XQ in per unit. So we take this value, we divide by the base impedance, and that will give you your XQ unsaturated in per unit. Okay. So going forward, the next part, I'm basically showing how you can get the saturated value of the D-axis reactance. And here I'm using the short circuit characteristic of that's given to us, and working out the stator current at this particular value. So at the field current of 2.84, I worked out what is the stator current, right? And from there, we can work out the saturated value of the axis reactance, and also I've converted it to per unit by dividing by the base impedance. So once you worked it out, then you can use this saturated value of the D-axis reactance to determine the saturated value of the Q axis. So we use the same constant, which is the ratio that we worked out before, and multiply it by the D-axis saturated value, which we worked out here, to get the Q axis, right? And again, you can basically convert it to per unit by dividing by the value of ZB. Right, so just to recap, you need to be careful. If we go back to the notes, as I said, when you're working out those values here, which is the unsaturated value, so remember that you need to use EDA, so from this point to here, to get your unsaturated value. And when you're working out the saturated value, we use ECA, so from this point to here, and that will give you the the saturated value for the D-axis. This is what I've basically summarized here. And also just be careful in terms of determining the value of the saturated value. So when you work out this value here, let's go back to this diagram, right? So as you can see, I have used this equation, the equation of line here of the short circuit ratio, to determine what is the short circuit current at this particular value here, right? So this current is very important. You need to use that to determine your current that you're going to use when you're solving for the current for the short circuit. So at this particular value, because you will see in the question, it's giving you the short circuit current at a particular value of field current, which is 2.2, right? And when you look at the air gap line, again, those value, which is the line-to-line voltage and the field current, you can see there they are 2.2, and for the short circuit characteristic, the open circuit characteristic, the field current is at 2.84, right? So in the solution there, you go back, right? So just be careful when you're solving for the value of the unsaturated value of the D-axis. So you must just be careful here. You see, I've used the rated value of the current here, okay, for the short circuit value current. And here, as you can see, I've worked out what is the value of the short circuit current at this particular value of excess field current, which is 2.84, and from there I've worked out the saturated value of the axis reactance. So just take note of that when you are solving for the saturated value and unsaturated value of the reactances. Right. So going forward, I will basically introduce the next concept that that we're going to look at for the next section that we will cover in the course. So it's just an introduction on the generalized machine theory. Basically, it's a theory that describes the machine characteristics in terms of a certain matrix that can be used to basically develop the equations for analyzing any electrical machines based on their connection, as well as what type of machine is it. For example, whether is it an AC machine or is it a DC machine. So this generalized machine theory, it basically develops a model that can be applied to either AC machine or DC machine. And from there, we can use this generalized theory to describe any machine, given if we know what is the type of connections they have. And for example, all the machine that you have basically discussed, we have looked at in machines 1 or machines 2, they can be modeled using this generalized machine theory. But now, due to limitation in the we won't get enough time to go through all the different types of machine. I will basically, in this section, for example, apply it in our tutorial to different types of DC machines that you have studied before in your machines 1 or your electrical principles course. To, for example, look at a separately excited DC machine or a series connected DC machine or a shunt connected DC machine. So either a motor or a generator. We will look at how, using this generalized theory, we can develop all the equations that are required to analyze the machine in basically transient as well as in steady state. Right, so as you recall, all electrical machines, they have those common properties. They have what we call a rotor circuit, or now depending on the machine, sometimes if it's a DC machine, we normally refer to this part as the armature, which is the part that's rotating. For a synchronous machine, we normally basically use the term rotor, which is basically mounted on the shaft of the machine. And on the external part, we will have what we call the stator winding. And in between the armature and the stator, we have the air gap section, which basically allows the magnetic flux from from the rotor onto the stator, or from the stator onto the rotor. It will pass through the air gap section. Now, since most of electrical machines have this common basically properties, so basically we can use the term stationary member, which is basically normally your stator side, and you have your rotating member, which is normally the rotor or the armature. And the air gap allows for this relative motion between the two. And the windings basically are both on the rotor side as well as on the stator side, and they are producing your flux that's is going to be required for operation of the machine. Now, this type of basically common feature that we have also they will have basically a certain type of connection, basically construction, to basically carry those elements. So you have your cylindrical ion, right, and core that's basically comprised of pulsating fluxes, and it obviously requires laminated material to reduce the eddy currents. And obviously, to basically complete the magnetic circuit, a certain magnetic flux will pass across the air gap from one member to the other and form what we call a closed magnetic circuit. Now, the narrow space that's between the two elements, what we refer to as the air gap, is the critical area of the machine. So the theory of the machine is mainly concerned with conditions in or near the air gap. And as we've discussed in the salient pole two-axis theory, you have the distribution of flux that's basically different in those two axes, and obviously that's due to the different reluctances along those two axes. So close to the surface of each element and running in parallel to the axis of the cylinders are these conductors that are embedded in the iron core, shown here, and this coil will obviously carry your currents, and the distribution of these currents around the surface depends on the operation of the machine. So I'll just basically summarize this part here. So in the general theory, we will basically is basically developed by replacing actual conductors by equivalent conductors located at the surface of the iron core. All right, so either at the center of a slot or at the edge of a salient pole, and this is the cross-sectional view, right, of the machine, and taken perpendicularly to the axis of the cover. So you will have those conductors that are on the this is an example of your cylindrical rotor, and you have your cylindrical conductors along in the slots of the cylindrical rotor, and these are your conductors on the stator side. Okay, so for example, here you basically have your north and your south on your stator side, and basically this can be further developed, right, to show the air gap circumference developed along a straight line, right? So when we look at this developed diagram, you can see that what's happening is between each of the pole, you have a flux density wave that's sinusoidal, and at the axis of the stator pole, you're getting the maximum flux density wave, and then basically in the interpole area, right, you're getting basically zero flux density wave, and then it goes into the negative axis for the south pole. Right, so basically we use this developed diagram to form what we call an equivalent two-pole machine, and we will use this equivalent two-pole representation to basically develop this theory. So just take note that one of the two physical arrangements that are shown above, they basically have concentrated concentrated coils around the pole, and then you have distributed conductors in the slots. So the behavior of the winding in the magnetic sense is divided into three groups. You have your flux pattern, which is stationary with respect to the winding, right? And then you have a flux pattern that's stationary with respect to brushes, that is, but not the winding itself. So that's a commutator winding. And you have a type of flux pattern that moves with respect to the winding. This is for a polyphase or a three-phase winding, right? So when we focus on this idealized two-pole representation that I said we're going to use to develop this generalized theory of the machine, right? We take a few assumptions. Magnetic saturation is neglected. The air gap, magnetomotive force, and fluxes are represented by sinusoidal fundamental components, and your magnetic material is free of eddy currents and hysteresis losses, and commutation is ideal. So the physical arrangement of the machine of two basic arrangements. You have concentrated windings and distributed windings. And so we will basically represent the machine in the following form, where we can write your Faraday's law equation here applied to a single coil. If you remember, E is equal to E N d phi by dt. Just take note that N times phi, that's number of turns, and that's the flux. That will give you lambda, okay? And lambda can be expressed as L times I, right? So that's the inductance times the current. So in general, both the inductance and the current will vary with time. So you can expand this equation into two parts. You have your EMF for a single coil into two components, L di by dt, and then you have I dL by dt. And this can be further simplified. So we're introducing the concept of the angle here. So we're expanding dL over d theta and then d theta by dt there, where basically the self-inductance when it change with the angular position, but the coils in the relative motion, the mutual inductance can be seen to change in a sinusoidal manner. So if d theta by dt is constant, the inductance can be expressed in terms of the angle rather than time. Right. So this part basically can be basically combined into a constant. Right. So the voltage of the coil, of one coil for a two coil system, basically will have two terms, your self and mutual inductance. So you'll have L1 here, you can see, and then you have M for the mutual inductance, right? And basically you can split it into those components as we've done before. And it basically ends up with basically three components. You have your resistance voltage drop, your transformer voltage, and the speed voltage, right? So if we look at the next figure, so it's showing you that you're getting a maximum, right, at 0 degrees, and then at 90 degrees, the voltage is basically, the mutual inductance is 0. So that's what we're basically saying, that now you can present the mutual inductance by this formula, which is M max times cos theta, where basically this is a cosine distribution where you're getting maximum at 0 degrees, right? And the voltage is M diz by dt. That's basically taking into account the mutual inductance. Right, so this concept basically, what we are interested in is taking this two-pole representation and basically derive a certain matrix that we can use for any machine. And you won't need to basically learn how to do the derivation, but you need to understand how the derivation is done. This generalized machine, or what we call primitive machine, it has two natural axes of symmetry. You have your D axis and your Q axis, right? So these are separated by 90-degree difference, right? And So this is an example in this figure here. If the armature are considered concentrated, as shown below, so they can be represented diagrammatically by a single coil, right? And so this is the coil that we are using to basically represent this concentrated coil representation. And the convention is that the current and MMF that the basically passing through the coil is taken as both is going into the same direction. So you'll find that the direction of the current is going into the coil, and also obviously then the MMF will also be in the same direction. Right, so the commutator action, right, effectively divides this commutator or armature winding electrically along the brush axis and into two uniform currents, right? And magnetically, your commutator winding behaves as a stationary concentrated coil, and thus your current in the coil produces a field which is stationary in space, and the voltage can be can be induced in this coil by rotation of a moving element. So if we look at this diagram of a two-pole DC machine, basically such a coil on the moving element, right? So if you remember your DC machine, you have your armature, which is moving, right? And then you have your two-pole on the and then you have your air gap. So the coil that's located on the moving element with its axis, it's basically possessing the two properties, is called a pseudo-stationary coil. So the two-pole machine can be represented in a diagrammatic form as two stationary concentrated coil. So as shown in this diagram here. So we have the Q axis and the D axis, and we have two coils, one on the Q axis and one on the D axis, right? So we're using the subscript IQ and VQ, so that's the current into the coil and the voltage induced in the coil, and we're using IF and VF for the axis, this coil, and so you will have basically IF and VF in this on this D axis. So this above concept can be extended to cover any number of coils on these two axes as shown in the next page. So this is a diagram of a four coil, a primitive machine with four coil, where now we have basically you have two pseudo concentrated coil on the moving part, which is the pseudo stationary coil. So we have IQVQ and IDVD, right? And on the stationary axis, we have two coils. That's basically that's IG and VG, and then you have VF and IF. So we basically have now in the four coil representation, you have on the D axis two coils, that's D and F, and on the Q axis you have two coils, Q and G, right? So you will see that this representation comes up to be basically all this will appear in our matrix that we will write, and this matrix we will basically use them to derive machines equations for a DC machine that we've studied before, and you will see that they basically produce exactly the same equations that you have studied before in principles and in Machines 1. Right. So what you need to take into consideration is that for the primitive machine, assumptions made, each coil may be subjected to a self-induced MMF, a transformer MMF, and a rotational MMF. So these are the three components so that we've shown in the equation. And the coils are stationary on the axis are shown so that coils that are on the same axis will have a mutual coupling, and coils on one axis has no transformer coupling with the coil on the other axis, and the pseudo coils on the rotating element have rotational voltage induced into them from the rotating in the flux of the next axis or in the defined direction of rotation. So these are the equations that we've derived before. So we've written them in that format. So you have for basically your coil F, you'll have those three components, and that's for the coil G. And again, remember that's your coil G, and that's D, and then Q and F that we've shown on the four coil primitive machine, and the speed voltages, right? So those speed voltages will appear, as I said, depending on the position of the coil, right? So when you basically now we've written the voltage for VF and VG. Applying this theory, you can also write the equation for VD and VQ, and it ends up with this matrix, as I said, which we wanted to derive, and it's basically showing you how the voltage induced in the F coil is related to the current that's being basically passing in that coil. So you'll have those two components that are basically relating the VF to IF, and so the voltage is equal to this matrix times this current matrix, right? So in your test, so this matrix is provided to you, so you don't have to go and derive it. It's given, but what we have to do is learn how to use this matrix and apply it to different machines to derive equations for that specific machine, right? So that is why I'm saying you need to understand how this matrix is formed, but the important aspect will be that you are able to use this matrix to basically then apply it to different machines. So again, from this matrix, right, and the equations for the voltage and currents, we can also derive the equation for the torque and power on the machine. So the developed torque by the machine depends on the currents, right, flowing in the windings, and the equation for the torque can be derived from the voltage equations by considering the instantaneous power. We used TE for the instantaneous electrical torque, TL your load torque, TF the frictional torque, and J is your moment of inertia. So the load torque plus the frictional torque will basically sum up to be equal to the total torque, and that's basically TE, the electrical torque, plus J times d omega by dt. Right, so using this, positive voltage and current mean that you're basically, this is the convention we are using in this derivation. When we have positive voltage and current, So it means that we are operating in motor mode, and because the convention is the current is going into the coil, and positive torque and speed if now is basically will show that we are operating in generation mode, right? So in terms of the general power supply to a motor, so it will be the sum of the currents and voltages, it's product of V times I, and you will have the three components. So Ri Lbi by dt, and then you'll have IDL d theta by d theta dt. So that is the voltage section, and multiplied by the current, and you end up with this R times I squared, which is your ohmic loss due to heat, your copper losses, and then you'll have I times L, and that's your basically the rate of change of your current in terms of time, and that's a rate of change of stored electromagnetic energy in the machine. And PE will be your related to the speed, okay, the speed related power available to produce the torque. So the three components, we're going to use them basically to determine the total power supply to the motor. Now, the speed power can be considered as power developed from an electrical origin. So, for example, in a motor operation, the total torque will be Te plus J phi by dt, right? And you can also convert Te into power. So you take it as Pe over omega there to get the total torque. Right, and you can also rearrange to get Pe as the subject of formula. And now if you consider the rotor coil, which is on the D coil only, the instantaneous power will be Vd times Id, and you can expand on the, so basically you substitute the full equation for Vd times Id, and you end up with this very long equation here. And just also the product of omega times the mutual, basically those mutual inductances, it will relate to IQ and ID for H and IG and IQ. So again, for the Q coil, you can also derive the equation for the power. So it will end up with this equation, right? And again, you will have power label for torque production using the mutual inductances, which is these values here. And the total torque will be the sum of VDID plus VQIQ, and you basically add both together, and you will end up with this equation here, right, which is P is equal to omega M dgig times ID minus M QFIQIFN IQ. Right, so this again, this formula which I've derived here, I will basically give it in the formula sheet, so you don't have to learn this very long derivation for getting the electrical power, which is for the torque production in the machine. So this equation will be given to you guys for your test. So just to recap, when we use this primitive machine model, so what we do is we draw the circuit diagram of the actual machine, then we determine the direction of rotation of the actual machine, and if the rotor speed or any of the current is negative, right, so different than that in the primitive machine, so we take note of that, and the machine equations will have to be modified. And for example, if it's a motor and then you want to operate this as a generator and where the current is coming out of the machine, so you have to take note of that. And then you're going to decide on which coils of the primitive machine will be used in the machine under consideration. And then from there, you can write down the equations using the matrix that I've shown you for the basically representing the selected coils of the primitive machine and eliminating terms that belong to coils which are not being used. Right, so you will see that many of the terms that are on the four coils matrix, we will basically delete them because they will not appear in our equation. And from there, we can write down the equations for the voltage, current, and torque, and represent the selected coils of the primitive machine. Step 6, then we will change the notation to account for the actual machine. For example, if it's field, we can use F for field. We can use F for field and A for armature, which are more familiar with you guys in terms of DC machine. And we will replace all these subscript, which is D, G, and F, and all that. We will replace them with notations that you're familiar with. And from there, we will have a basic set of equations to describe the machine at any condition, whether it's transient or steady state. Right. So once we've done that, we can transform these sets of equations by eliminating time-dependent terms. So that's when we want to work them into steady state. And we'll replace the instantaneous voltage and current variable by capital letters to indicate that now we're representing the machine in steady state condition. And also, we can use the steady state equation to develop equation describing the machine characteristic that you're interested in. For example, if it's a motor, you're interested in the torque speed characteristic, so we can use this equation to derive that. Or if it's a generator, then you're interested in the terminal voltage versus the load current, so then we can derive the characteristic of that. So those exact steps, we will basically go through them on Monday using examples. So I will enable the tutorial on Moodle for you guys to have a look and give it a try. And then on Monday, we will go through the tutorial questions and explain to you how this primitive machine model can be used to derive those equations. All right, guys, so I will stop here and we'll meet on Monday for our next lecture.